So I'm going to explain where pH, pOH, where that comes from. It has to do with the fact that if you look at water, okay, as it turns out, water does what's called self-ionization. And if you have a sampling of a whole bunch of water particles, like I got this beaker full of water, so this is bloop, 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 bloop. Itself, water itself, breaks up into a hydrogen and a hydroxide ion. Not very many of them. So let's say I got, zillions and zillions of water molecules making up that beaker full of water. Every once in a while, there's going to be one water molecule that will break up into what we have defined as an acid and what we've defined as a base. Well, it's not a big deal. You don't notice it because you always have equal amounts of acid and base when it breaks up. These are always equal. But just the same, water does break up, and it's called self-ionization. Self-ionization. And what it does is it determines the pH or pOH, the realm, the range at which a solution can be either acidic or basic. So how this works is, okay, I'm going to go back to this equilibrium, and I'm going to handle it just as if I were handling any equilibrium. Once I see that it's an equilibrium from the reversible arrows, I can write a mass action expression. So the mass action expression would be the concentration of the hydrogen ions times the concentration of the hydroxide ions over the concentration of the water that I started out with. But wait a second. Water is a liquid, okay? Liquids aren't included in mass action expressions, so it simply is the concentration of the hydrogen ion times the hydroxide ion. That's going to equal K, just like every other equilibrium. This K is sort of special, though, so it's defined as Kw. And as it turns out, it has a value of 1 times 10 to the negative 14th. Okay? So that 14 right there defines the lower limit of the pH scale. And I'll show you how that works. All right? So I'm not there yet, but I'm getting there. So I'm going to go through and I'm going to look at a sample of pure water. If it's pure water, I know that the hydrogen ion concentration will equal the hydroxide ion concentration because those are both coming from one water molecule, so they have to be equal. Since these are equal, I can set them both to x, solving this mass action expression right here. X times x is equal to 1 times 10 to the negative 14th. That means x squared is going to be equal to 1 times 10 to the negative 14th. That means x is going to be equal to 1 times 10 to the minus 7th molar. So for pure water, okay, sample of pure H2O, the hydrogen ion concentration is going to equal the hydroxide ion concentration. Okay, and together each one of them is going to be 1 times 10 to the minus 7th molar. Well, that you can see that's a puny little number. That's 0.00000001 molar. And that's why when I drew the picture of the beaker and I had the little dots in there, there's not a lot of little dots in that sample of water. Well, I'm going to keep going on this pH deal. So what exactly is pH? pH is equal to, and it's just a math deal, the negative log of the hydrogen ion concentration. What's more, there's something called pOH. We don't use it, chemists use it, but normal people don't use it, which is equal to the negative log of the hydroxide ion concentration. Okay? So if I have a pure sample of water like I did before, where the hydrogen ion concentration equals the hydroxide ion concentration, and each one of them was 1 times 10 to the minus 7th molar when I solved that equation. To find this pH will be equal to the negative log of the hydrogen ion, which is 1 times 10 to the minus 7th molar, which turns out to be 7. Well, that 7 is a neutral solution on the pH scale. 7 is neutral because when it's 7, it also means that the hydroxide ion concentration was 1 times 10 to the minus 7th. So the pH scale ends up looking like this. It goes basically up to 14, down to 0. 7 is in the middle. If I have an acid right here, it means, according to my equilibrium, and I should get that, let me draw that. Let's get rid of pure at this point, pure water. Okay. And this pH is 7, get rid of this. Go back to the equilibrium, the self-ionization of water, which was H2O going to H plus OH minus. Alright? The mass action expression has to equal 10 to the minus 7th. So this times this has to equal 1 times 10 to the minus 7th. No, not minus 7th. Minus 14th. Because it's the product. That's the K now. Looking at how Le Chatelier's works, if I have more of this, I'm going to have less of that. When I have more of these, it is an acidic solution, and the concentration of it, of the hydrogen ions, is going to become greater. So that's why anything from 0 to pH of 7 is considered an acid, because I have far more hydroxide ion or hydrogen ions in that solution. The hydroxide ions correspondingly go down because the product of both of them always has to equal 1 times 10 to the minus 14th. Now on the other side of the scale, 7 to 14, now this is pH that I'm defining right here, because pH would be opposite of this. A base, this realm in here, goes the opposite. At that point, I have a heck of a lot more hydroxide ions than I do hydrogen ions. The product of those two multiplied together still has to equal 1 times 10 to the minus 14th, but it would be down in here. Now if I looked at a POH scale, nobody uses that, but we could. There's no reason why POH isn't used. 0 here, 14 here, 7 is still neutral, because when it's POH of 7, it means that the H pluses equal the OH minuses. But now, when I'm 0 to 7, this will be a base, because it means I have more hydroxides than I have hydrogen ions. And when it's from 7 to 14, means I don't have a whole lot of hydroxide ions. Now I'm going this other way. Now I have less of those, and I have more of these, so it becomes an acid. Right? But we don't really use POH, which is except in chemistry. And here's a handy little relationship. POH plus pH will always equal 14. And that's a math deal, and you can do that on your own and figure that out. Alright? So last little thing, if you have a hydrogen ion concentration of 1 times 10 to the minus 6th, the negative log of that is going to give a pH equal to 6. That is that. Okay? And it'll get more complicated, but for now, that's good enough.